Every single day, a massive network of satellites quietly captures thousands of images and measurements, giving us a continuous, real-time feed of our planet. We are pulling in optical photographs, bouncing radar signals off the surface, and scanning the topography with 3D LiDAR lasers. But instead of giving scientists a perfectly clear picture, this mountain of information has actually created a bottleneck. Gathering all this data is paralyzing the people trying to use it. Looking at this diagram, we can see the core issue: multimodality. A two-dimensional photograph, a radar pulse, and a climate simulation are structurally incompatible formats. Because they don't natively speak the same language, scientists are stuck manually cross-referencing these siloed datasets to find basic correlations. When researchers are trying to map an uncharted ecosystem to protect biodiversity, or public health officials are trying to predict the exact path of an urban flash flood, they hit a wall of friction. What should be a rapid, fluid analysis to respond to a crisis turns into a grueling process that can take weeks or even months of manual labor. We are collecting enough information to track global crises. Our problem is that we lack the translation tools to actually read that information in time to act. To fix this, Google DeepMind built AlphaEarth Foundations. It functions like a virtual satellite, acting as a universal translator for all of this disconnected planetary data. This illustrates the model's strict spatial standard. It slices the entirety of the Earth's land and coastal waters into uniform 10 by 10 meter squares. Once established, AlphaEarth takes the optical imagery, radar, and climate readings and weaves them into a single cohesive data block. By locking the entire planet into this standardized framework, the model can look at any given location and clearly track how it evolves over time, frame by frame. Establishing this 10-meter grid solves the structural chaos, but to make this massive amount of data actually usable, the system has to compress it. AlphaEarth processes the deep well of information inside each of those squares and generates a highly compact digital summary. This shows how the model creates an embedding, mapping the vast data of a single location into a specific mathematical coordinate on a 64-dimensional sphere. These summaries are so remarkably efficient, they require 16 times less storage space than previous methods. Yet this extreme compression doesn't sacrifice precision. AlphaEarth achieves a 24% lower error rate than other mapping systems, even in scenarios where labeling data is incredibly scarce. It can cut through persistent cloud cover in places like Ecuador to detail agricultural plots, or map the highly irregular, notoriously difficult terrain of Antarctica with absolute clarity. We now have a unified, extremely lightweight digital format that AI systems can finally process natively. This compression and unification organizes the entire planet into a searchable, high-speed database.
Google is now pairing these data sets with the advanced reasoning capabilities of Gemini to power Google Earth.
This integration allows anyone to query the Earth's physical systems using simple, natural language, like asking which communities in the Democratic Republic of Congo face the highest risk for a cholera outbreak. Or you could ask the system to instantly locate every single storm drain within 50 meters of a public school in Brooklyn. Organizations like Map Biomas use this structure to dive deep into vital ecosystems like the Amazon, precisely monitoring environmental and agricultural changes on a massive scale. In public health, researchers at Harvard and Boston Children's Hospital are utilizing similar population dynamics models to pinpoint exact gaps in measles vaccinations down to the individual zip code level. Major global institutions, including the UN's Food and Agriculture Organization, are actively adopting these resources to classify completely unmapped environments and direct their conservation efforts. Analytical workflows that once required years of iteration now take minutes, providing the immediate, actionable intelligence needed to protect the physical world.